Before 2002, the cosmos was exclusively government territory. National space agencies like NASA and Roscosmos held a monopoly on orbital flight, backed by massive national budgets and thousands of legacy contractors. The foundational math of this era was highly inefficient. Every mission required a bespoke, multi-million-dollar vehicle that would burn through its fuel, detach, and fall into the ocean as debris. Because of this approach, the capital requirements to build a rocket were astronomically high. When combined with the near certainty of explosive failures during development, private aerospace startups were widely considered a financial death wish. Decades of this methodology created a stagnant market. The global aerospace industry had simply accepted exorbitant launch costs as an unchangeable law of physics. When Elon Musk established SpaceX in 2002, he anchored the company to a singular, distant objective: reaching Mars. To make that viable, he proposed a basic logistical shift. If a rocket could deliver a payload to orbit, land vertically, and fly again days later, the cost of space transportation would drop to a fraction of the traditional price. Aerospace veterans quickly dismissed the radical concept. The consensus was that a small, privately funded team lacked the resources and legacy knowledge to execute a vertical landing of an orbital-class booster. SpaceX was operating on a fraction of a typical government space budget. Attempting reusability meant directly challenging the engineering foundations the industry had relied on for 50 years. The early reality of that challenge nearly destroyed the company. Between the years 2006 and 2008, SpaceX's first 3 attempts to launch the small-lift Falcon 1 rocket all ended in failure. By the fall of 2008, the startup had burned through its initial capital. Musk's reserves had dwindled to the point where there's only enough funding left for exactly one more launch attempt. If that 4th rocket failed to reach orbit, SpaceX would have to declare bankruptcy and close its doors immediately. On September 28, 2008, the 4th Falcon 1 cleared the pad, survived stage separation, and successfully reached Earth orbit. Surviving that final test flight proved the private orbital model was viable. It immediately caught the attention of NASA, which awarded SpaceX a massive commercial resupply contract, injecting the cash needed to keep the company alive. With their immediate survival secured, the engineering team shifted focus to scaling up. They began developing the much larger Falcon 9. Their development cycle operated on a simple loop: build prototypes rapidly, test them to failure, analyze the data, and quickly iterate. This iterative process eventually solved the reusability problem. First stages of the Falcon 9 began returning to Earth after delivering their payloads, touching down vertically on autonomous drone ships. Recovering those multi-million-dollar boosters drastically reduced the cost per kilogram to orbit. It also allowed the company to turn around and launch vehicles at a pace national agencies could never match. Today, the Falcon 9 architecture handles a staggering percentage of global space traffic, carrying regular commercial payloads, scientific instruments, and crewed missions to the International Space Station. By engineering a booster that survives the trip to space, SpaceX broke the long-standing financial barrier to orbit. But dominating low Earth orbit is only a stepping stone. His stated objective has always been building a transportation system to make humanity multi-planetary. That requires Starship. Designed as the largest, most powerful rocket ever constructed, it's built to haul immense cargo and crews across interplanetary distances. Pushing the physics of a fully reusable, super-heavy launch vehicle has resulted in highly public explosions during early test flights. Internally, engineers view these destructions as intentional stress tests, yielding crucial flight data to refine the next prototype. Building the rocket is only one piece of the logistics. A permanent Mars settlement requires solving massive biological and technical challenges, including deep space radiation shielding, reliable food production, and long-term life support systems. Developing technology to survive those conditions, combined with the sheer scale of the Starship vehicle, makes the Mars program a highly uncertain, multi-decade gamble, requiring vast amounts of capital. This presents a critical business problem. Development costs for Starship are measured in billions of dollars. To prevent the company from falling back into the financial peril of its early years, SpaceX launched the Starlink satellite network. By providing global internet connectivity, Starlink acts as an independent revenue stream, shielding SpaceX from relying solely on launch contracts to fund Starship. Unlike traditional startups depending on one product, this diversified ecosystem distributes financial risk. While this internal fortress subsidizes the push toward Mars, It creates a common misconception about the exact nature of Elon Musk's personal fortune. He is frequently cited as one of the wealthiest people on Earth, but a closer look at the data forces us to ask if he holds the liquid cash required to see this vision through.